Hello, I am Seema and welcome to part 42 of the chapter Organic Chemistry, Some Basic Principles and Techniques. We were doing the quantitative analysis of organic compounds, and in the previous video I told you how do we determine the mass percentages of hydrogen and carbon in a hydrocarbon. Moving ahead with the same discussion, we now come to the next element that we would like to determine, and that is nitrogen. So how do we determine the mass percentage of nitrogen in the organic compound? Or if we find out in the qualitative analysis that nitrogen is present in the compound, then how do we go ahead and find out what is the mass percentage of that nitrogen in the compound? In order to find out the presence of nitrogen, there are two methods that we use. One is known as the Dumas method and the second is known as the Gel-Dals method. In this video, we are going to be discussing only the Dumas method, and the Gel-Dals method would be done in the next video. So let us come to the discussion of what do we do in Dumas method. You remember when we tried to determine carbon and hydrogen? If you do not remember how we did it, I would encourage you to watch the previous video. We took, in a combustion tube, we took the compound and we burnt it kind of in excess of oxygen. In this case, what we do, we heat the compound up in excess of carbon dioxide, or in an excess supply of carbon dioxide, or when carbon dioxide is being given into the combustion tube, we heat up the compound. So in Dumas method, the compound is heated with copper oxide in an atmosphere of carbon dioxide. So you have copper oxide in the compound. Copper oxide is present in the ignition tube, and the compound is also present, and carbon dioxide passes through it and we heat it. So you see different zones are there. First is copper oxide gauge. A gauge of copper oxide is present. Then copper oxide and the organic compound has a layer. Then there is coarse copper oxide in one layer, and then there is a reduced copper gauge in the end. So we make sure that throughout the entire column you have copper oxide present. So the compound is heated with copper oxide in an atmosphere of carbon dioxide. We do not put in oxygen here, rather we allow carbon dioxide to come into this apparatus. And when you heat the compound with carbon dioxide in the presence of copper oxide, a reaction takes place where the copper oxide, it oxidizes the hydrocarbon. And when the oxygen from the copper oxide is used up, and the copper oxide gets reduced and it oxidizes the hydrocarbon. And as a result of its oxidizing the hydrocarbon, it oxidizes carbon and hydrogen, and nitrogen gas is released. This nitrogen gas is then collected, and then we collect the nitrogen gas and we find out its mass. I'll come to that later, but let us first see what happens. What is the reaction that takes place? You have C6H5NZ. So in the hydrocarbon, assume that the number of carbon atoms is X, the number of hydrogen atoms is Y, and the number of nitrogen atoms is Z. Then copper oxide, the oxygen from copper oxide is going to oxidize carbon and hydrogen. So resulting in the formation of carbon results in the formation of carbon dioxide, and hydrogen results in the formation of water. So the formula that you will get will be H2O. So if you have Y number of hydrogens, how many hydrogens, what would be the formula of water when you have Y number of hydrogens? It will be HY by 2O, right? It will be the number of water molecules would be Y by 2. I hope you get this. So since it is Y, 2 hydrogens make 1 water molecule. So the number of water molecules that you would be getting would be Y by 2. So you'll get Y by 2 water molecules. Therefore, the number of copper oxides in order to reduce for the balanced chemical equation, in order to oxidize hydrogen would be Y by 2 number of copper oxides. And if there are X number of carbon atoms, then every carbon atom is going to get 2 oxygens from copper oxide to form carbon dioxide. So twice X, 2 times of X and half of Y number of oxygens should be there in copper oxide in order to balance the chemical equation. This is theoretically balancing the equation. while you're doing it in the furnace, or in the furnace, you're not actually going to be counting the number of molecules. You're just going to have copper oxide, but that is the number of copper oxides which would be involved in reaction. So in the chemical reaction, we write the exact number, what is going to happen. So if you have C6H5NZ, then every nitrogen molecule is N2. So if there are Z number of nitrogens, obviously the number of nitrogen molecules would be Z by 2. So that is what we see. It's a very simple equation. Only the alphabets that have been used in order to generalize it may make it appear a little complex. It is not. So C6H5NZ reacts with 2X, twice of this, plus half of Y, copper oxide. It results in the formation of X molecules of carbon dioxide, Y by 2 molecules of water, and Z by 2 molecules of nitrogen. And the copper which is left would obviously be 2X plus Y by 2 copper oxide molecules were there. All the oxygens were used up. So what you're left with is 2X plus Y by 2 copper atoms. So in the end, you get the reduced copper oxide in the form of copper, right? Which you see here in the copper gauge, the reduced copper gauge. The reduced copper oxide, it is present, it gets settled here. And now beyond this, what is formed is only gases. You get water, you get nitrogen, you get carbon dioxide. The copper gauge stays with the copper remains with the copper gauge, and the gases now pass through the combustion tube. And when they pass through the apparatus, they enter this tube and they come into this new apparatus which is known as the nitrometer. The nitrometer has a mercury seal in it, and it is a tube which is calibrated, and in the tube you add potassium hydroxide solution. When you add potassium hydroxide solution, and not all of it, you don't fill all of it, you just fill it, let us say to, okay, yes, you do fill all of it. And when you fill it up with potassium hydroxide solution, and you have an outlet here, and potassium hydroxide solution is also present in a trough or in another vessel on the other side, to which the tube is connected. Now, why have we done this? The atmospheric pressure, do you see it's open here, but this is sealed here. So if potassium hydroxide is present till the top, the atmospheric pressure is pushing this down and it fills it up to the top. Now, the calibrated tube is filled up with potassium hydroxide solution, and the mercury is present to seal it so that this potassium hydroxide does not go backwards into this apparatus, or it is not wasted here. We want to accurately measure the volume of nitrogen produced. Since nitrogen is a gas, here we will be getting the volume of nitrogen. So we need to get the volume of nitrogen, therefore we use the mercury here to seal it up. As the reaction takes place, the gases, they can pass through this, but water cannot go back through the mercury. So the gases, they come in and they enter the potassium hydroxide solution. We know that carbon dioxide is soluble in potassium hydroxide. So the carbon dioxide which is produced will automatically get dissolved in potassium hydroxide. But the moisture and what was the other gas? Nitrogen. The moisture and the nitrogen, some of the moisture due to the difference in temperature, because the potassium hydroxide is colder in comparison to the moisture or the water vapor which is coming from here. Some of it may dissolve, but some of the water vapor and nitrogen will get collected in the tube up on the top. How would it get collected? Because as gas forms, it rises upwards, it pushes the level of the potassium hydroxide solution downwards. So it kind of occupies the top of the tube. By the downward displacement of water, the gas is being collected. Since we don't have water, we'll say by the downward displacement of the liquid, which is potassium hydroxide solution. So what will happen as the gas which is building up here, it exerts pressure. As it exerts pressure, it pushes the potassium hydroxide solution down, and the potassium hydroxide solution starts moving here towards the other vessel. So the level of potassium hydroxide keeps on increasing here, which is being pressured by the atmosphere. The downward force here is the atmospheric pressure. So the atmosphere is pushing this down, but the nitrogen is pushing it outwards, and thus when both the pressures become equal, at that time the level of KOH will become stable. Or when all of the nitrogen has been released from the sample that we took, the volume of nitrogen will now become fixed. Once the volume of nitrogen becomes fixed, our experimental part is over. We needed to find out the volume, and since this tube is calibrated, we now know what is the volume occupied by nitrogen. The only glitch here is that we don't have pure nitrogen. We have some amount of moisture also. The carbon dioxide we got rid of by using potassium hydroxide because it dissolved all the carbon dioxide. But the moisture, some of the moisture is still present in the tube. So you can calculate the volume because the volume is fixed, but the pressure being exerted is not only the pressure of nitrogen, it is also the pressure of that little moisture that is present. We'll come to that discussion later. But let us right now understand that the nitrogen is collected over the top, and that is how we know what is the volume of nitrogen collected. And from the volume of the nitrogen collected, we will be calculating the mass of nitrogen present in that sample, and from that mass, we are going to calculate the mass percentage of the nitrogen present in the compound. So this was, oxides of nitrogen are also formed, but they are reduced to nitrogen by passing over a heated copper gauge. Some of the oxides of nitrogen that may be present, they will also be passed through a heated copper gauge. This copper gauge is also in the furnace, so that even if some oxides of nitrogen are formed, they will break down and they will result in the formation of pure nitrogen. And that is how you collect all the nitrogen that is given out by that compound. And nitrogen is collected over a solution of potassium hydroxide. Now I'll wipe this off in order to explain the mathematics of the Dumas method. Give me a minute. Let's now do the mathematical part. What are we aiming at? Let us first see that. We have found out the volume of nitrogen, and we have found it out at room temperature. But we know what is the information that we have, and how can we go about finding the mass of nitrogen from the volume of nitrogen. We know that at standard temperature pressure conditions, we know the mole concept, and if you really relate it to the molar volumes and the molar masses. 22.4 liters of any gas at standard temperature pressure conditions weighs equal to its molar mass. Its molar mass and 22.4 liters of a gas, they at standard temperature pressure conditions are the same. So we would say that 22.4 liters or 22400 milliliters of nitrogen at standard temperature pressure conditions would weigh how much? It would weigh 28 grams. This is the information we have, that 22400 ml of nitrogen weighs 28 grams. Okay. Now we have the volume of in the nitrometer. We have collected the nitrogen, and we know its volume because it is calibrated, and we know exactly what its volume is. Using this information, we are now going to find out its volume at standard temperature pressure conditions and then use it to calculate our mass. So we know that P1V1 upon T1 is equal to P2V2 upon T2, right? Let us say at standard temperature pressure conditions, this is P2V2 upon T2. At STP, at standard temperature pressure conditions, what is T? T2, in other words. What is temperature? Let us say this is the experimental conditions, the pressure, volume and temperature. I'll come to that, the pressure part, later. But what is the pressure at standard temperature pressure conditions? What is the temperature? 273 Kelvin is the standard temperature. And what is the pressure? Standard pressure, P2. Standard pressure is 760 millimeters of mercury, right? 760 millimeter mercury is P2, and T2 is 273 Kelvin at standard temperature pressure conditions. What we don't know is V2, right? Let us say this is not V2, it's just V. It's just naming, we don't want the digit 2. So we'll just say what is V. From this we want to calculate V. V and V1 are different, that is clear to you. So if I want to calculate V from this, V would be equal to P1 V1 upon T1 into T2 upon P2, right? All I did was cross multiply, take this there, V remains where it is, and from this we calculate this. Do you see here? And what is T2? If you substitute this, this would be equal to P1 V1 upon T1 into, what is T2? Is 273 Kelvin, and P2 is 760 millimeters. Why have I deleted the units? Because if you really see, you will always get the volume in milliliters here, right? And the since we are going to relate it milliliters or liters, which we will be converting using this. Since we have taken this as ml, we'll assume that what we are getting is milliliters. So the units would, as it is, get cancelled because this is just a ratio. So we'll just put the values here. P1, V1, even if you did put the units, they would get cancelled and you would get the, for volume, you would get the milliliters in the end. So this was what you get. Volume P1 V1 upon T1 is equal to into 273 upon 760. P1 and V1 are the pressure and volume of nitrogen that we have calculated the experimental conditions. But P1, the pressure that we get here, is not equal to the atmospheric pressure. You know, why are we talking of atmospheric pressure? If you notice in the apparatus, in the other vessel, we had kept the other vessel open. And I told you the atmospheric pressure is pushing it down. So the pressure of this experiment is equal to the atmospheric pressure. But in this column that we had, we did not have only nitrogen. We had a little bit of moisture also. So when gases exert pressure, if nitrogen is exerting the pressure, the gas that is present is also, that is moisture, is also exerting some pressure. So when we calculate P1, P1 should not be just the pressure of nitrogen. It is actually the sum of, according to Dalton's law of partial pressures, P1 is actually the sum of the pressure of nitrogen and the pressure of moisture present. So in order to know the pressure of nitrogen, you will have to calculate the pressure, the atmospheric pressure minus the pressure of moisture. And this pressure of moisture is known as aqueous tension. That the water, whenever you collect a gas over water, some of the water molecules would always be present, and those will exert their own pressure. So that pressure is known as the aqueous tension. So you will have to subtract the aqueous tension in order to get the value of P1. So P1 is actually the total pressure of the two gases minus the pressure of aqueous tension, the pressure exerted by moisture, right? So we say P1 and V1 are the pressure and volume of nitrogen at pressure, and the pressure P1 is not equal to atmospheric pressure at which the nitrogen is collected, because P1 is actually equal to the atmospheric pressure minus the aqueous tension. Whatever is there, when you have a numerical, you will be given the aqueous tension, or you will be expected from all of it to be calculating it, although very rare that they would go in the opposite direction. But if they do, to make it a little more complicated, you can still calculate the aqueous tension. Anyway, atmospheric pressure minus aqueous tension will give you the pressure of the nitrogen collected. Now we know the pressure P1, we know, and from this we have calculated VML, the exit, using the new value of P1, not the P1 that we assumed what we calculated there. But P1, or rather the pressure minus aqueous tension, will give you P1. So after having crossed that hurdle also, now what do we know? We know that 22.4 liters or 22400 milliliters of nitrogen weighs 28 grams. So we will start with this, that 22400 ml of nitrogen weighs equal to 28 grams. Now we are calculating from the volume, we are going to calculate the mass of nitrogen. Once we get the mass of nitrogen, then we can calculate the mass percentage. So it is 28 grams. Therefore, what is the volume? What is the volume? The volume is V. So 22400 ml of nitrogen weighs 28 grams. So 1 ml of nitrogen will weigh how much? 28 upon 22400 grams. And V volume, how much would it weigh? It would be 28 upon 22400 into V grams. Why have I avoided the units? Both the volumes will have the same units and the units will get cancelled. So we'll only put the numerical value here. So now what from this, by using unitary method, you have found out what is the volume. So from the volume, we have found out what is the mass of nitrogen. After having found out the mass of nitrogen, we will again use unitary method to find out the mass percentage. So from this information now, we will calculate the mass percentage of nitrogen. Now whatever nitrogen has been prepared, this is the mass of the nitrogen that has been prepared, but we know that this is the mass of nitrogen which was prepared by reacting m grams of the compound. So now we know m grams of the compound had how much nitrogen. From that we will calculate that if in m grams it is this much, what would be the mass percentage? In 100 grams, how much would it be? So we'll use unitary method again and we'll say that in m grams of the compound, nitrogen, the mass of nitrogen is 28 upon 22400 into V grams. So if there was 1 gram of the compound, in 1 gram, how much would it be? It would be equal to, you will divide, if this is the mass of the compound of nitrogen in m grams, in 1 gram it will be divided by m. And what would it be in 100 grams? In 100 grams it will be into 100. This will give you the mass percentage of nitrogen. Right, that is what you see here. Percentage of nitrogen is 28 into V upon 22400, which is the volume, the mass of the compound in m grams. So in 1 gram it will be divided by m, and in 100 grams it will be into 100, which will give you the mass percentage. Right? So this is how you would calculate the mass percentage of nitrogen by Dumas method. Now we'll be doing a numerical problem. Give me a moment. Now this is a problem, the solved example that is given in your text. The question reads that in Dumas method for estimation of nitrogen, 0.3 grams of an organic compound gave 50 milliliters of nitrogen collected at 300 Kelvin temperature and 715 millimeter pressure. You have to calculate the percentage composition of nitrogen in the compound. So it is, let us see what all is given to us first. So for the method of estimation of nitrogen, the mass M is given to you is 0.3 grams of an organic compound gave 50 ml of nitrogen. So V1 is equal to 50 ml. Okay, of nitrogen is collected at 300 Kelvin. So T1 is equal to 300 Kelvin. These are the things that are given to you. And the pressure is P1 is 715 millimeters of pressure. But 715, how do you calculate P1? You calculate it by the pressure that you get minus the aqueous tension. So aqueous tension is also given to us, which is 15. So 715 minus 15, which will be equal to 700 millimeter Hg is the pressure. P1 is 700, right? And at 300 Kelvin, we've already written 715 mil. You have to calculate the percentage composition of nitrogen in the compound, and this is given to us. What do we know? We know that 22400 milliliters of nitrogen weighs 28 grams. Okay, this is the information that we have from which we are supposed to calculate the percentage composition of nitrogen in this compound in 0.3 grams of the compound. So what do we do first? What did we do first? We will find out the volume of the nitrogen if it was at STP, because we have done this at 300 Kelvin. It is not standard pressure temperature pressure condition. So we need to first find out the volume at standard pressure temperature pressure. So we'll say P1 V1 upon T1, or let me just take it down from here because I need not derive it. So what would be the volume of nitrogen at STP? Volume of nitrogen at STP would be equal to P1 V1 into 273 upon 760 into T1, right? So let us substitute all the values. P1, what is P1? Is 700. What is V1? Is 50, and into 273 upon 760, and what is T1? Is 300, right? I've put all the values. This is the volume of nitrogen at STP. From this you'll calculate the volume of nitrogen at STP, and when you calculate this, what will you get? The volume would be 41.9 milliliters. 41.9 ml would be the volume that you will get. So this is the volume of nitrogen at STP. We know now, from the volume, we are supposed to find out the mass. So we know now that 22400 ml of nitrogen weighs 28 grams. So 1 ml will weigh how much? 1 ml will weigh upon 22400. You divide it by 22400, and 41.9 ml will weigh how much? It will be into 41.9 grams. So the ml and ml will get cancelled. So this, you'll get the mass in grams, which would be equal to how much? It would be, okay, we'll leave it as such because we are going to carry on the calculations further. Now this is the mass. This is the mass of the nitrogen that is produced by reacting m grams of the compound. And what was m? M was 0.3 grams. Now using this, we will use unitary method again and find out the mass percentage. So we'll say by reacting 0.3 grams of the compound, or 0.3 grams of the compound has nitrogen equal to 28 upon 22400 into 41.9 grams of nitrogen. So 1 gram will have, you'll divide this by 0.3, and 100 grams will have into 100. That will give you the mass percentage, and when you calculate all of this, it will come out to be 17.46. 17.46% will be the mass percentage of nitrogen by reacting 0.3 grams of the organic compound. So this is how you would solve this numerical. I'll give you a moment to take a screenshot. So I moved on aside for this. And with this, I'll wrap up today's video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.